Welcome to LonTI. Today we have Ulf Lindsröm, who is a Leverhulme visiting professor at Imperial College, and he's going to tell us about supersymmetry, complex geometry, and the Hyperkähler quotient.
I'm very pleased to be here. Thank you. And I realize that there's a lot of background material I have to go through. So the actual Hyperkähler quotient won't be until next Monday. But we're going to work through some of the background material so that it's easy to understand the construction starting today. And I have no idea what kind of background you have, except some of you. And I was told that this should be for students. So bear with me if I'm too elementary. Okay, so the first thing I want to say is that I had prepared slides for this. So I have them on my computer, and then I was told that it's supposed to be a Blackboard talk. So for that reason I have put my laptop here, and you can all take bets on when I'm going to stumble over it and fall, because that looks very probable. Okay, so I'm going to start with defining sigma models. So a sigma model is a theory of maps from some domain into a target space, right? So phi is the map, and we have coordinates on this domain, and then phi of x act as coordinates on this one. So there are more than one phi, of course, more than one x, but this is being schematical. And that's not all that goes into the sigma model. Also, you have to give it, you have to give the action or field equations. So you need to specify that these maps, they extremize the following, again, schematic action. So the important thing here is that there's this symmetric two tensor here, and here these are the derivative with respect to x, for example, and then I wrote dot dot dot, and that's because after that we can, if we're writing a supersymmetric version, there will be spinorial terms, etc. But this would be of phi, by the way. But this is the key thing. This is the hallmark of a nonlinear sigma model. Nonlinear because of this metric is a function of phi as well.
Do you allow it to have a trace?
To have a
trace for G?
At this point, I am not specifying anything more than that this is a symmetric one. And of course, if you can have more tensors if you want. And for example, in 2 dimensions, you can have a B field, as we all know. So this is that, and then the field equations that you get are from varying phi, are just G mu nu d squared phi nu plus, and here's an important term which is d phi rho gamma rho sigma nu times again the phi sigma. So that's the format. That's only looking at this part, which is the one I say define the sigma model. And what I want to point out from this is that clearly G mu nu symmetric tensor you can think of as a metric on the target space, and here's the Levi-Civita connection for that metric. So already at this stage, just writing down a bosonic sigma model, we see that this has something to do with the geometry on the target space. Okay, so in this case, when we haven't specified things more than this, it's as a Riemannian geometry, of course. But depending on the dimension on sigma and the amount of supersymmetry, which I haven't introduced yet, the target space geometry gets more and more restricted, and that's what we're going to use to our advantage in this discussion, because it means that constructing a sigma model of with certain symmetries automatically constructs a certain geometry on the target space. So that's one key that we have to. I mentioned, of course, the fact that in 2 dimensions we can have integral we can have a B field, so we can have G mu. I'm still going to be very sketchy about the derivatives here, but it's going to look like this: G mu nu plus B mu nu phi nu, and this is an antisymmetric tensor. So we actually have one part which is symmetric and one part which is anti-symmetric. This should have a the phi nu. And this, my main interest is in the 4-dimensional case, or high-dimensional. So I'm not going to say a lot about this B field. It's just that it shows that actually the geometry you get for 2-dimensional sigma models is in some sense more interesting than for higher dimensions. This coupling you can only have in 2 dimensions. Okay. And okay, so in this case, when you introduce this B field, I'm talking about the geometry, and the geometry is if you look at these equations that you get from this model, when you include a B mu nu, then this here, the connection is no longer the Levi-Civita connection. It is the Levi-Civita connection plus torsion, and the torsion is given as the field strength for the B mu nu. So I'll just write it that H is the B in form language. I'm not being careful about the coefficients, etc. I'm just sketching the general situation, and that's interesting, and that means that we have more possibilities in two-dimensional sigma models and the geometry on the target space than otherwise. Okay, to continue. Maybe I should state my goal here. What I want to do is I want to use, first of all, I'm going to stay in 2 dimensions just because things look a bit simpler there. But I'm going to focus on the case where B is 0. And then what I'm going to do is to study the quotient for a bosonic sigma model. So I'm going to look at this kind of sigma model in 2 dimensions. I'm going to assume that it has isometries, and I'm going to look at the quotient space for the model with those isometries. And we'll see that will, of course, well, not of course, but it will preserve the geometric structure here. So isometries will be important. So the isometries will give the infinitesimal version of that. So we'll give d phi mu, and we'll call that the parameter epsilon, and k mu is the generator of the isometries. And we can have more than one. So if I introduce a label for that, this is the way that the isometries look infinitesimally. And then we also will be assuming that we have a Lie algebra. So Ka Kb is equal to Fab C Kc, where so Ka I should write this is then K mu A d by d phi mu, and this is the bracket here is the Lie bracket.
K is the label K comes over what?
Oh, and this is a d-dimensional Lie algebra.
The coordinates, local coordinates.
The local coordinates we're assuming runs from 1 to d, capital D. Okay, but it's important that the algebra of the isometries can be non-abelian like this. Okay, so now what are the isometry? What's the requirements on an isometry? The requirements are of course that the Lie derivative along K of the metric vanishes. And just to keep on commenting on 2 dimensions, you might have thought that it's the Lie derivative of B that should also vanish, but that's not true. It's in fact H that should be invariant, where H, as I said, is the field strength for this B. And this becomes important when gauging it, and maybe I can indicate that, because if we look at this one, it will have one term which is okay, I epsilon k dh plus di epsilon k h. So that has to be 0, but we already know that this is 0, the field strength. So this is the condition on H. So if we look at what that means in terms of B, we find that the Lie derivative on B has to equal a total derivative D and on a vector plus this action here, which gives me EK on B. And it's this V, when you're gauging these sigma models, that becomes an important issue. That you have to take care of that. That changes the, for duality, for example, it changes the Boucher rules and so on. But this is just a comment. We're not going to stay with that.
I have a question for me. Is the fact that H equals to be a local or a Bruegel statement?
This?
No, H equals to be on the other side.
That is a local statement, yes. So B is only locally defined. It's actually a gerb, but that's beyond this. Okay. So anyway, I should say that gauging the sigma model and gauging the isometry of the sigma model will be important in two different contexts. One is the one I'm interested in today, which is the quotient construction. The other is, of course, in duality, when finding a dual theory. So, and that's where I said that this becomes important. We'll only be interested in the quotient. So when you do duality, you will need to add a term to the sigma model after gauging it that puts the field strength to 0, and that term we're not going to include, of course. Okay, so but now we want to look at the situation when the parameter, which is a constant here, becomes I used it upstairs in a function of the fields. Sorry, I'm using different notation here. This should be of phi. So, no, this was correct. X is the domain coordinate. So, this is what we want to do, and then, of course, what we do, as usual, we have to introduce something that compensates for the derivative of this. So we have to introduce an A field, which did I use coordinates on this one? Yeah. So I introduce a field A. This is not reading this very well. A is Lie algebra valued, of course, and it's the variation becomes d epsilon A minus f A B C A C E D epsilon D. This should be B, C, C, D. Okay, so what that says is the usual stuff. There's this term which is to compensate for the x dependence when we vary the action, and there's a term which just says that A transforms in the adjoint of the algebra. And then we introduce we have to introduce covariant derivatives. I'll write this as plus plus is equal on phi mu is equal to d plus plus on phi mu minus a mu a. Now didn't write the indices here, but it will be plus plus in this case, and it's Lie algebra valued, so k b mu. Okay, so then the action becomes integral d to x. We're in 2 dimensions now. D plus plus phi mu g mu nu d minus minus phi nu. So replacing the derivatives, I'm sorry, I'm standing in front of the blackboard, replacing the ordinary derivative with the covariant derivative as usual. And this is the gauged action, and now we want to find the quotient. And that proceeds by integrating out A. We extremize, we find that the connection A that extremizes this field, and sorry, this action, and then that turns out to be, well, I have all the gory details here, but I'll just give you the net result, which is that A plus plus minus minus is equal to HCB KB mu G mu nu D plus plus or D minus minus on phi nu, where H, so this is the inverse of HAB, which is K mu A G mu nu K B nu, okay, which gives this as an inverse. So this is just you just plow ahead and do the variation, and you find the field equations for A, and you can solve it in this form. But then this means that S becomes integral d to x d plus plus phi mu g mu nu as before minus a term which is K mu A H let's go to the next slide. It should actually be this H A B K nu B D minus minus phi nu. So this is just doing what I said. Solve for A to find something that extremizes the action, and that's that H. Sorry, that A that's written down there, and then you plug it back in, and you get this, and this is now a new metric, and this is the metric on the quotient space, because with this metric only sees the orbits of the isometry. So this is the metric on, if we call the manifold M and the isometry group G, it's this. Okay, so it looks a bit like we've broken the local symmetry. We haven't. This is just one particular, this is just introducing one particular connection A. So this is still locally, it still has the local isometries, and it's just choosing a particular connection that does this. But this has produced for us a model and a geometry on the quotient, on this quotient space. And that's the archetypical way of finding new geometries. So we start from one geometry on choose a geometry, simple geometry, say that just flat space, and then we gauge the isometries. and then extremize it. To get a particular A, I'll call it A, with twiddle, and then plug back. So this is in fact the whole story, how you get from one maybe simple geometry with isometries to a model on the quotient space, this one. So why is this useful? Well, it's useful. This is all done in the bosonic case, but for the supersymmetric case, as I said, the geometries will be very much more restrained. So in 2 dimensions we have left and right supersymmetries, and the supersymmetries are characterized by that Q left and P right, say. And if we look at the supersymmetry here, the number of supersymmetries, what we've looked at is really no supersymmetries, but the one with just one left and right is no different. We don't get a new geometry for that. But if we have two supersymmetry and still have G and B, we get something called bihermitian, but if we cross this out, we'll be more interested in the Kähler case. Right? And similarly, in the 4-4 case, with G and B, we get hypercomplex, bihypercomplex, but we'll be interested in this case, and that's Hyperkähler. So the whole project then is to start from to understand how you gauge a Hyperkähler manifold or a Hyperkähler symmetry, which is a 4-4 supersymmetry of an action of a sigma model. You have to understand how you introduce the isometries that are compatible with that situation, and you have to understand how you gauge these isometries, and then how you take a quotient. And so in principle, you're just doing this, but you're doing it in such a way that supersymmetry is preserved, and in the specific context of 4-4 supersymmetry.
Is there an 8-8?
Sorry?
Is there an 8-8?
In 2 dimensions, you mean? Well,
wherever you want to be.
No, 8-8 supersymmetry, you'll get, it won't be a sigma model at the lowest, there will be a higher spin, right?
Okay, right.
So you wanted to remove, you want the bosonic part. You want the bosonic thing to be just, but that's an interesting idea, though. Maybe. Okay, So the Hyperkähler quotient then, which we're aiming for, is we start on in a Hyperkähler manifold of a simple kind, and we look at the 4-4 supersymmetric sigma model with that target space geometry, and then we need representations of supersymmetry, of course, and we need a sigma model with this 4-4 supersymmetry, and we need killing vectors compatible with the supersymmetry, so isometries that are compatible with the supersymmetry, and a supersymmetric way of gauging those isometries. So that's the aim of this presentation, to provide that.
So the manifolds so far smooth and compact.
Yeah,
So So you have to do some change of coordinates?
To do what?
One patch to another patch?
Yeah, the transition functions.
Transition function.
Yeah.
So this description is all local, right?
It's local.
So how do you think about this, the patches?
Well, that's a whole other issue, but that's the issue of whether you can gauge something and get a global gauging, and that is possible, but it's not, you know. I don't want to get into that because it's a complicated issue, but I can give you the references to that.
And another question is, in case there are singularities, the action is not well defined?
No, this is we're thinking of this as a singularity of the isometries, you mean, or of the metric. The metric is by definition smooth everywhere.
I see. So it's
that's a global. The metric is global. Yeah. I can do both actually, but it's okay. So now we're going to get into supersymmetry. So I'm sure most of you, a lot of you at least, are experts in supersymmetry, so you can turn off now. So what I'm going to do is just going to quickly remind you, recapitulate what it is. So we have the Poincaré group with the Lorentz generators, the translations, and we add Q and Q bar, which are anti-commuting supersymmetry generators. And we write this as, and we really only need the algebra, which is P++, and similarly for a P minus minus. And this is in 2 dimensions, and it's 2,2. That's why I have these guys are complex. Okay. And you remember that if you look at Minkowski space, you can realize these as differential operators. So, I've introduced notation that I haven't explained. Okay, so plus and minus are just spinor indices, but double plus and double minus are vector indices. So that's based on this particular situation in 2 dimensions where pairs of spinor indices are vector indices. And when I write it like that, I'm thinking of the light cone actually. So these are light cone. I've gone to light cone coordinates. So let's say this is x1 and this is x0, and then I introduce x++ and x minus. And what I do when I go to Minkowski space, to Minkowski superspace, is that I extend this, so I have x++, x minus are my bosonic coordinates, but I add to these theta plus, and in this case theta bar plus minus. They are anti-commuting spinorial coordinates, Fermi coordinates we used to call them. And I'm not going through exactly how you do this, how you get to superspace. There is a technique using induced representations, which is how you can also define Minkowski space if you want, as the quotient of Poincaré with Lorentz. And this is this space is the quotient of super Poincaré by Lorentz. Okay, so then the fields, these acts on P++ is I said it's a differential operator, so it acts on phi of x plus plus x minus minus, and now we extend that to superfields. So we have phi of x plus plus x minus minus theta plus minus theta bar plus minus. Okay. And having done that, we also expect to be able to represent these Fermi operators as differential operators. That's, in fact, part of the reason why going to superspace is good. And so we will represent Q plus minus acting on a phi of x theta bar as a differential operator, d by d theta plus minus. I haven't told you what that is, but you can define that. Plus I times theta bar d plus plus, this plus minus minus minus. That's a very compact notation. Sorry about that. Acting on phi. So d by d theta, that's the Fermi coordinates are funny in the way in this way that they're the derivative, which I wrote here, is actually the same as the integral. So we'll see later on that how these can be used as to get a measure on superspace. And there are, of course, two different options when you define these. They can act from the left or from the right. These are acting from the left. And that brings me back to what I said about the induced representations, because there are also two ways of doing that. One way leads to these Q's being represented like this, and the other way to another set of differential operators, which are d and d bar. There's the so-called spinorial covariant derivatives. I have them here somewhere. So I'm just doing plus plus. So they also form the same algebra, and similarly for minus. But the key thing is that these operators, for all values of these, they anti-commute. So that means that imposing some constraint on a superfield using these spinorial derivatives is something which is covariant with respect to these to the supersymmetries. So how can we use that? Well, in 2 dimensions, we use it as follows. That a general superfield, which is what I wrote down here, is not an irreducible representation of supersymmetry. So we have to constrain it somehow. And the way we constrain it is using these spinorial differential operators. We use these precisely because that the supersymmetry is preserved, the Q supersymmetry. And there are a number of ways of introducing constraints in 2 dimensions. The most important one, which carries on to higher dimensions, is this. That's called chiral superfield. Chiral superfields obey this.
Do you want plus and minus on that, or just one?
No, these are chiral, so it's plus and minus. Okay. Yeah, it's spinor index. That's the way. And then there are a number of others, and we won't be concerned with them. But there's twisted chiral, which obeys a more different conditions for plus and minus, just like you mentioned. That's the twisted chiral, and there are also semi-chirals, which obey only one of these, and also the complex linears, which obey things like this. Oh, not phi. Well, I should call it something else, because phi I reserve for these chiral guys. Okay, but it's these are the ones we'll be interested in, because they're the ones that also exist in higher dimensions.
So the objects you said are all irreducible, or some of them are still reducible?
Well, I mean, to write down one way, you see that you need to have some constraint if you want to write down a sigma model, is if you write down a sigma model in terms of this general field, it will contain vectors as well, which you don't, so it will not faithfully mirror the bosonic case at the lowest level.
But the semi-chiral and
semi-chirals are guys that obey these constraints. That's a left semi-chiral, and this is a right semi-chiral. So you see, they're weaker constraints. The chiral ones obey both plus and minus equals 0.
So then would they be irreducible under the supersymmetry?
No, they actually have a, no, they're more, they have, okay. Next time when I talk about generalized Kähler, I'll show you. Okay. But but these have, the chiral ones have components, and when I say component, I mean the Minkowski space components that are part of the superfield. And there's a very useful way of finding those, so I'll just write that. So the components I find by setting the thetas to 0. So the lowest component, which is just a function of x, is phi of x theta bar at theta and theta bar equals 0. So this means to set these to 0. And then the spinors, psi plus minus of x, is the, and here again we use the covariant derivatives. This is this at theta is 0. And then finally f of x is equal to d plus d minus acting on phi and setting that to 0. So in terms of Minkowski functions or fields, there's a scalar, there are two spinors. This is actually a pseudoscalar, which is it has the wrong dimension actually to be a physical field. So it's an auxiliary field. You integrate it out to get your action in terms of the components. Okay, so action. So I should say what the action will be. The action will be something like this. for chiral fields. Okay, I have to explain this. This goes back, and I also put, I operate with these on here, and then I put theta to 0. This goes back to what I said before, that the d by d theta are funny guys. This is actually the same thing as writing d2 theta, d2 theta bar for the Berezine coordinates. So that this is the measure, and k is just the most general function you can think of. So just a general scalar, real function of and scalar, of course, of the phi's. And when I write phi with a capital A, I mean if I have numbered them, indexed them, I mean this. Okay. So this is the function. This is the superspace action in 2,2 language, and but we introduced the components, so we want to see what this is in Minkowski space, and the way to do that is to actually reduce in 2 steps. One way of doing it is that. So we can reduce it first down to 1,1. I keep saying 1,1, 2,2, etc. And I remind you, this here is in 2,2, which means it has 2 left and 2 right supersymmetries. And we're going to reduce it to 1,1 and then reduce it to components which we can call just 0,0 if you want. No supersymmetries. So the first step is to reduce to 1,1. So that's this. And you do that by separating your covariant spinorial derivative. You see they're sitting here. So you write that as 1/2 d plus minus minus I q plus minus. So the d plus, the first one here will be the 1,1 covariant derivative. So that's that one. And when you've reduced it to 1,1, only that part is manifest. So there will be additional non-manifest I'm not sure extra supersymmetries is a good way of stating it. It just means that when you write it in 1,1 language, so 1,1 superspace, you will have the 1,1 supersymmetry, one left and one right, manifest because it's written in terms of those superfields. But there will also be an additional symmetry, which is of the action which is generated by this. Maybe it'll become a little bit clearer when I do the reduction. So what we need for the reduction is to rewrite this one, but also to know how this act on our fields, on our chiral superfields. So let's do that. We have d plus minus on phi a is 0, which is equal to d plus minus on phi bar a bar, which is 0. That's the chirality constraint. Now we can read off what that means for Q here. So it means that Q plus minus, if I combine the two, is equal to JAB d plus minus phi b. And JAB is simply I times 1, I guess, and minus I times 1. So this is a complex structure in canonical coordinates. Which is a hint, because it means that the phi's are the canonical coordinates for this complex structure. So we'll detail complex geometry later on, but here let's just say that this is how it is introduced, and we can use this because to evaluate this guy, because this guy now is integral d to x d squared q squared with some factor that I'm not bothering with, acting on k of phi a. So now what we have to do is we have to evaluate that part. Then we will get the 1,1 action, which has measure, which is d2x d squared. So I'll have to do that over here, I'm afraid. So we're pushing in the Q's, and we're actually using, we're pushing in the Q's and then using this relation. There will be some terms which have to be partially integrated as well, but I'm not going to bother about that. I'll just give you the net result, which is this, that the action becomes d2x d squared. So that's the measure, and then we have d plus phi c k. So now I'm using small letters. That's not easy to see. B perhaps, B bar, D minus phi bar B bar, plus complex conjugate. And this KB bar is important. It's the dk d phi b d phi bar b bar. And in fact, what we want, this is a typical 1,1 action where this is the metric. So in this language, the metric has a potential, and it's the metric is the second derivative of that potential. We're not quite allowed to call this, to know that this is a metric until we've actually reduced it down to its bosonic part, where we see that it's actually the metric. So we keep pushing these in, and we use the definition of the components to find that this becomes a mess. Well, first part is not so messy. It's d plus plus phi a g, well, a b d minus minus phi b, and there are terms which couple. These are not very illuminating. The extra terms, they're of the sort psi bar, psi nabla. Okay, I'll just indicate what they're like. It's psi plus a, and then there's a covariant derivative. This also has a GAB. So there are terms that couple derivatives to the spinor derivatives. This should be plus. And more of them. And then there's this funny fermion term, which looks like this. I can write it exactly. So that's that one. But the point is what is interpreting this and reading off what it becomes. So we find that GAB is actually the derivative of so GA, like I wrote over there, AB bar is K comma AB bar. So that's two derivatives on the potential K, and you find gammas, which are part of this, and curvature, which also corresponds to this. So this says that the geometry is complex and that it's Kähler. We already saw that it's complex due to a complex structure, and it's actually Kähler because it has this potential. And also these geometric structures here that enter are of the right kind to be Kähler. Okay, so it's just reproduces Kähler geometry as
this is after the integration of the
auxiliary field, yeah, F, yes, that's a good point. I meant to say that, yeah. So we have eliminated F. Okay. So next, I want to take a closer look at complex geometry and say how Kähler geometry is special in that context. But I want to have a look at, maybe we should take a short break. What do you say?
Yeah.
Okay, let's start again. And we ended up with some complex geometry, Kähler geometry. And I want to spend a little bit on discussing that in more detail. So we have a manifold which is even dimensional, and we have an endomorphism J. So it just acts on the tangent space.
That's the dimension, right?
Sorry?
When you say two-dimensional, it means real dimension or complex dimension?
This is even dimension. It's a real dimension. It has to be.
Just visible by real dimension.
Yeah. It has to be even, and that's very clear from this. What I say now, that J squared. This is an endomorphism which squares to -1. So if you look at that in with indices, that says this, right? And of course, that's only possible in even dimensions. You take the determinant of both sides, you see that. So it has to be even dimensional. It has M, and this has to be true. And then if you I'm calling it a complex structure, but it's actually just, at this stage, it's just an almost complex structure, because complex structure comes with the condition of being integrable. So we'll discuss that now. Once we have this J, we can define pi plus minus. Is one way of writing it, and it's this 1 plus minus ij. So now this is in real coordinates, and now we've extended the tangent space with the complex numbers to be able to write this. And it's once we have this is a projection operator, as you can convince yourself. It squares to itself, both of it, and it can be used to look at the tangent space. You can split the tangent space into say u and v are vectors in the tangent space. You can look at the projection of these guys, and you could ask if you combine those in a Lie bracket, is that still of the same kind? You take one, if you call that t plus and t minus, one in t plus, another in t plus, is their Lie bracket still in t plus? So the question is pi minus plus of this 0? If it is, the distributions they define are involutive, and the condition for this, if you work out simply this, is that how does it go? J, I, K, no, J, L, K, comma, I, M, and anti-symmetrized here. Can you read this? L, K, it's a very minus M exchange K is 0. This is a condition you get from working out this thing, and you actually get it 2 times. And this is, if you think of this as a 3-index tensor, it is the Nyenhouse tensor. So it's this M, K of J, and when then so that's the condition that this holds, is the condition that this one vanishes. Nyenhouse tensor. And it means that integrability. It means that you have integrability of these distributions. You can think of it as being able to put together the tangent spaces at different points and in a smooth way, such that this holds. So this is integrability is the vanishing of the Nyenhouse tensor, and that's a theorem by Newlander and Nirenberg that proves that, in fact. But the way we're using it is simply to say it's integrable if this J is integrable if this vanishes, and interpretation is that this is true. Okay.
How could that expression not hold? That looks on that.
Which one?
Your pi minus plus on the commutator.
No, it's pi minus.
Because you have pi minus plus minus is always 0.
But this is a Lie bracket.
Is there not a distributive property?
It's no. I mean, you get derivatives, right? From this you get derivatives on this, and from this you get derivatives on this, and that gives you an index which this one acts on, and then you read off this. Okay.
Why did you have 2 weaknesses?
Sorry?
So why did you have 2 weaknesses like that?
I have 2. This one. Here.
No,
here.
The G anti-commutation.
L comma K.
Oh, here.
derivative.
Oh yeah, oh I'm sorry, yeah, that's a derivative, comma k. I'm sorry. This is a mistake I often make. I always take for granted that the extra indices are derivatives. Sorry. All right, so that's one thing, but this was in a manifold with one of these j's. So when I should say that as well, that when J satisfies this, it's called a complex structure, and we could also have a metric. G. Okay, so then this we can ask about hermeticity with respect to this complex structure, and that hermeticity says that this holds. Okay, this is transpose, and it means that omega, which is equal to G, so you lower one index with a metric, is equal to minus its transpose. So there is a two form, which is so it's antisymmetric is a two form, which comes when you have a G and a complex structure. And I should really write this in canonical coordinates, and you'll recognize it, because that one I've already done, but the metric will be when it satisfies this with this complex structure. This just looks like this. Let's call it, don't know what indices I'm using, phi bar, phi bar, phi bar. Okay. So, and you go, of course, you can also write this out in terms of the metric here, components. This omega is called, in the context of Kähler, when we have G equals 2 derivative on K. So I'm now writing Kähler. The conditions for this to be Kähler. So then you have the omega is 0. So it's a symplectic structure. And you also have the covariant derivative of J is 0. This is with respect to the Levi-Civita connection. And you have, most importantly, the phi bar is d2k d phi bar. So that's the sort of thing that we found when we looked at the sigma model, and this condition, once you have this given, that it has its 2 derivative on the potential, then you just plug that into the form of omega, and you'll see that this vanishes, d on this vanishes. It's straightforward. And you also see something else which is important, that k is only defined up to so modulo f of phi plus f bar of phi bar. That you see from that's certainly, these certainly don't contribute to the metric. If you look at the sigma model, these are these terms, you remember it's gone now, but the sigma model is just has a 2 derivative on this potential. So this is the 2,2 sigma model. So clearly, if you change this by f of phi plus f of phi bar, then that's annihilated by this, because the bar on phi equals d on phi bar equals 0. So the sigma model and the metric, and in fact the whole geometry is only defined up to these kind of transformation. That's going to be very important later on, because if we talk about isometries, then it's not enough. I mean, you can talk about the case when K, the potential, is invariant, but if you want isometries, this should be invariant, and that means that the whole action can just variation of the action or variation of K can go into one of these f plus f bar, which is called the Kähler gauge transformation. So what we're saying is that K in the sigma model and in Kähler geometry is only defined up to a Kähler gauge transformation. Becomes important when we're doing the gauging. And just to compare to this, remember that this is the Lagrangian of the model. This is the Kähler potential for the geometry, and the Lagrangian is the Kähler potential. That's important. Okay. So our goal, so we have studied the 2,2 sigma model, and we've discussed that it corresponds to Kähler geometry. We really want to study 4,4, but there's no formulation in terms of superfields or superspace where we have 4,4 manifest. There is actually, but no, projective superspace. Okay, harmonic superspace. There is, but you have to add additional degrees of freedom to the space. So the way you want to study extra supersymmetries is to start from a Kähler model and impose that it has additional supersymmetry. If you do that, you can get the results for Hyperkähler. So to look at that, we just start by again writing down the 1,1 form of this Kähler sigma model.
So, do you allow interactions besides what we saw here, of the form of 2 theta integration? Sorry,
do I additional superpotential here? Yeah. No, I don't. Well, you can discuss that as well, but not in this context. So I just remind you what the 1,1 version of the 2,2 sigma model looks like. Maybe I'll just write the reduction. So it's this. But when we reduce it down, it becomes okay, let's do that. D squared. This is, we've already had this on the blackboard. Okay, so to find the 2,2 supersymmetry, you can start from this 1,1 superspace action and ask for additional non-manifest supersymmetries. We derived that previously in going down from this one to this. We derived the Q, but alternatively you can start directly in 1,1. Start directly from this, and you make an ansatz for an additional supersymmetry. The reason I'm explaining it this way is that that's the avenue that works for the Hyperkähler one. So this will be generalized to the Hyperkähler. So this is epsilon plus minus, and here's, you make an ansatz where this is some function so there's an epsilon plus and an epsilon minus transformation. So you make an ansatz for the transformation. You haven't said anything about this object, and you haven't and you need to use this action to do that. So so what are the conditions you need to impose on a supersymmetry? Okay, it's closure of the algebra. Otherwise, it wouldn't be a supersymmetry. And invariance of the action. And these are both needed to pin down what kind of animal this J is. And so it follows from closure of the algebra, says that if we take two variations, such variations of a field phi, it should go into minus epsilon 1, epsilon 2. So the 1 and 2 are the two transformations. And then there's a D on phi, where this is the ordinary partial derivative. This is supersymmetry, just stating supersymmetry, somewhat sketchy. And invariance of the action says that del S has to be 0. So from the closure, from this one, from the top one, we find this, and in fact also the Nyenhouse tensor vanishes. So from the closure of the algebra, we find that J is a complex structure, and from this one we find that J transpose J is G, so the hermiticity condition, and also that the covariant derivative with respect to the Levi-Civita connection is 0. So we find all these things that characterize Kähler geometry from this. Okay. Right, so in our case though, this is not enough. This was enough to start from a 1,1 and find out what the conditions are for having extra supersymmetry that gives us 2,2. It gives us Kähler. So now what we do, we want more supersymmetries. And then we have to modify this ansatz, and the modification is with, okay, I'm running into notational problems here. Delta phi A, remember capital A is denotes phi and phi bar, and then this has to be epsilon, and since I'm going to do more than one supersymmetry, I'm going to do 3 supersymmetries, an ansatz for 3 supersymmetries. So I'm going to call this X, or maybe I is better, I. And it has a plus minus. So there I runs over 1, 2, 3. And then of course, correspondingly, I have 3 J's. So this is, in condensed notation, is my ansatz. Okay, so I runs over 1, 2, 3. So clearly, we'll find one of the complex structures that we'll find is the same as we just derived, but there will be 2 more. So we'll have 3 complex structures, actually 4, given the ones that just is built into the story with complex conjugation. So what we find is that we find that from closure of the algebra, we find that they're all complex structures. For all 3. And we also find that Ji, so the metric is Hermitian, with respect to all the complex structures. And also we also find that they're all satisfy this, the covariant derivative. Okay. So we find all of this, and we find something more, which is important, which is that we find that there's a relation between these complex structures, and the relation reads Ji Jb equals delta AB, no, minus delta AB plus epsilon A, B, C, J, C. So the complex structures satisfy an SU2 algebra, the algebra of the quaternions. And that, of course, is a hallmark of the Hyperkähler geometry. So, yeah, I don't know. Maybe this is a good point to stop, actually, because I'll go through this one slide that I have on Hyperkähler, which might be useful. So, because this is not the full story, it turns out that if you have if you take a linear combination of these, then this is again a complex structure, provided that A squared plus B squared plus C squared is 1. So in fact, that is a useful observation that the complex structures, they form an SU2, and it's actually a full two-sphere of complex structures. And yeah. And then, of course, you have more than one Kähler form. Remember, Kähler form is G times is G times J. So this is, here you have 3 Kähler forms. And yeah. And this, they all satisfy this. They're all symplectic structures. And I think that's the next thing I want to do is write down, tell you about the isometries for this case when you have a sigma model which has 4 supersymmetry. And that will take us quite a bit. So I think we should stop here.